Hello everybody, today we'll be doing word ladder. In this problem, a transformation sequence from word beginning word to word end word using a dictionary word list is a sequence of words begin word S1, S2 to SK such that every adjacent pair of words differ by a single letter and every SI for 1 through I less than K is in word list. Note that begin word does not need to be in word list and SK is equal to end word. So given the two words, begin word and end word, and a dictionary word list, return the number of words in the shortest transformation sequence from begin word to end word, or 0 if no sequence exists. So let's decipher what they actually mean here, and let's look at one of the inputs and outputs. But essentially, like overall, we're looking at one word that's called begin word and end word, and we're trying to find a way to change one letter at a time until we get to this last word. And here we have an output of 5. How we did that was that we had a hit that had similar characters to hot, as you can see here. There's also dot, dog, lot, and log, and cog. Okay, so as you can see here, hot has a HIT, and we have this word is similar because it has two of the same similar words, which is HOT. Are there any other items that look nearly the same? And I don't think so. You can change one letter that looks the same. So no, so that's the only option. So we go from hot to hot, hit to hot. And now when we have hot, we can also get dot, or we can also get lot. Those are the possibilities because we only have to change one character. Or we can change log, dog. No, those are not possible. So we're gonna test either lot or dot. We can try both. So that's the BFS call. And so we're looking at a BFS. Like we're gonna try. So we have two opportunities now to select the right count, and we don't know which one we're gonna find out, which one's the one that's better. But if we want the dot route, we could get dog, or we can get we can get dog. If we went lot, we can get log, as you can see. So those are possibilities for us. Whoops. Those are only possibilities for us. And either way, with dog or log, right? Because we just changed the G, we can get to cog by changing one character. So this is how our items will visit. So first, this is our first count. Second, third, fourth, and fifth. So it took us 5 BFS moves for us to get to cog. However, in an edge case where the begin word and the end word is not in our items, right? So we were gonna output 0 because it is impossible to get to, because cog is not in the word list. It is impossible. It could also be impossible if we look at these items, and there would be no way for us, even if we branched out and did every single item. Let's say that there was no hot, right? I don't think we could have gone anywhere. Like it would just not have happened. Like hit would go into blank. There would be no way of changing it, and we would get 0 as well. So that's another possibility, another case. So let me put that down as one of the cases. And I think like we can think about edge cases, like what's the min word of begin word and end word? Are those actually words? And those types of things would be good to think about, right? Is this even possible? And to ask those questions, that's important, I think. So let's look at the begin word and end word. So the begin word has to be of 1 character to 10 characters long. The end word is equal to the length of the begin word. And the word list is of length 1 through 5,000. So there must be something in here. And basically it tells us that we don't need to handle any of these weird edge cases that are possible, like no item in the word list, or like no item in the begin word or end word or of different lengths. Because if they were, then we can just also return 0 immediately. And so those are good questions to ask, like, oh, are the begin word and the end word the same length? Are there words in the word list, to make sure that you don't get to make sure that this thing is possible, and so on and so forth. So with that, I think everything is a lowercase character, so there's no need to lowercase anything. And begin word does not equal end word. All words in word list are unique. Okay. So I guess one easy question to ask for interview. So what are we working with here? So like, what's the begin word? What can it be? What are the possibilities? End word. What are those possibilities? What are possibilities of what we can get in the word list? What are the types of constraints that we're working with our problem? And the constraints are pretty good. So let's those are only the edge cases that are possible that we need to handle because of the constraints that we have been given. So, I mean, you can make the constraints extremely wide and we'll never finish the problem. So, here we go. What's the time and space complexity that I believe that we'll take? So, time and space complexity is O of n times n. So, it's like, why is it n times m? So, I'm looking at n being the word length, and m being the actually, so number of words in the word list. So why is it m times n? So for each word in the word list, if the word, right, in the beginning word is of length like 10, right? There are 10 different ways, patterns that we need to look at for us to seek in the word list. And every one of those words in the word list needs to be seeked as well. So here's what I mean. So let's say we have hit, right? And that's our first word. So what are the patterns that we have to check? So we have hit, we have hit, and we have hit. So we can change this a star into anything we want, but we have 3 possibilities. So this is the length of words, and we have to do this for only the first word. Now, we have to do this for every single word for us to get to the final answer. And so we're doing this for a hit, we're doing this for a hot, we're doing this for a lot. So, I mean, because hot, we're seeing this, we see OT, right? So that's not a pattern. Then we see H star T. Those are the same pattern, right? And we have HO, and the last one here. So that's 2 times 3, the length of the word already. And we're doing this for every single word, right? So because we have this and we see this pattern match, we have HOT and HOT. Because those match, we can move from we can move from here, hit, to this word hot. We can get this pattern, right? And we can get this word, and from this word we can look at all of its patterns, excluding this one because it's indivisited. And we can look at these possibilities. So by looking at these possibilities here, we can get lot and dot. So here's what I mean by getting that, lot and dot. So I think this is very good to go over. It's going to take some time, but I think it's important because This way we cover how our algorithm works in terms of our plan and in terms of our matching. Because we're already, like, from talking about the time and space complexity, we're already developing a solution, and we're already using a visited set that we need to know. Visited set. We're using adjacency lists because we know that of type list, because we know that from this particular word, the pattern, we can get multiple words, and if we need to use all of those words. So visited words and patterns or words. Patterns or words, we don't know which yet. I would say patterns, because we don't want to reuse the same patterns again. And yeah, that's the same as getting the same words. It's all the same. So right, with adjacency lists, we know that we will be getting a list of words, like pattern to word, right? To words. So that's what we're looking at already. So let's see what's next. So what's next is that, right, we're going to do this BFS style. We already know that we're doing this BFS style from this particular understanding. So we're looking at BFS already. And those are lots of things that we glean from just learning about this problem. And so what else are we looking at? So we have dot, right? That's going to be the same OT, as you can see that right there. And we have D dot T. We're just going to go down one path, and we're not going to go down both paths at this point. So to save the time, so D, O, and T. So what we see here is that we can try out this pattern, right? And this pattern, they're the same. So we can get this dot word. And once we have this dot word, we can go into looking at all of its patterns. So we got dog. And basically dog has this OG pattern, this DOG pattern, and this DO dot pattern. So with this, we can dot, we can visit these items here, and by visiting this item, we found dog, right? Because these are the same. Once we look at the pattern, and we can reverse look up our word from our adjacency list that we have built. So I mean, at this point, remember to plan at the same time. So we're gonna build adjacency list with all patterns to words. Okay. So lastly, what we have is cog, right? We already know that, and we have OG, we have CG, and we have CO star. So this is called star, and because the OGs are the same, we can pull cog, and we find the word, right? If we run BFS and find the word, return count, run the BFS and increment count, we're gonna build a visited set of patterns, so they will not be revisited. Why we want patterns instead of words, though, I was thinking it didn't matter, but does matter, because if we did words, we would have the same patterns again, and would start seeing the same, bring up the same words, and would actually go backwards sometimes. Because let's say we have DOG, right? And we look at OG, and of course that's cog and also log. So we could go in that direction, and we would be doing some weird stuff, and we would be repeating our work. Yeah, because log also has OG as well, and it will create problems. So they're not big problems, because I mean eventually you hit the word and it's just a little bit more work, I think. Of course, we have to run through a logic, but we don't have time for that. We're running at 15 minutes already, and so we're running out of time. So let's keep on building. So we have our visited, and we have our point. And if like after BFS of all patterns and not found, return 0. Also, if like remember that point where there is no end word, if end word is not in word list, return 0. And what else do we have? We have built adjacency lists. We built the visited sets. We run the BFS, increment the count, and add items to visited sets. Items as in patterns. What else do we have? I don't think we have anything else. And increment the count. I think that's it. That's the whole entire plan. We have an example that we can look at when we're coding, and we have like lots of information to glean on. So I think with that, we are ready to do our code. Let's just grab this and move it up here so that we can use it while we're coding, and we can get started. So first things first. So if end word not in word list, return 0. Okay, that's done. So check. We can throw this part away, or signify that it's done. Okay, let's use something nice. Let's can I cross it out or like something, or like I don't know. Okay, we'll just do a couple of these. Okay, so build an adjacency list. Okay, so no problem, we can do that. So we're building an adjacency list with all the patterns. So word list, we're doing this for every item in the word list. So we have to add begin word into the word list. So word list dot append begin word. Okay, so that's exactly what we'll be doing. So let's write that in. So for word in word list, we're going to create a adjacency list. So adjacency list is equal to default dict of list. Okay, looking good. And so for each word, what we're going to do is break up the word, and for j in word in length of range length of word, what we're going to do is adjacency list at we're going to create the pattern, which is equal to the word from this point to j plus, let's say, our pattern. We can do any character. Let's just use star because it is a universal like symbol for like substituting any item into the word. So we can do that, and j plus 1. So this skips a word. And so basically what this does is that it goes up until j, but not including j. So which is like, say, 0. And we just add the star, and we want everything else after that. Also, it takes in the next word, hot. Like, I mean, if it's j is 1, we basically skip 1. We go up, it takes 0. And so basically we get like if we had hits and j is 1, we take h and we skip the middle item, and then we have the last item, so hot, and we have to skip the first item if j equals 0, and if j equals the third one, then we have the last item if j equals 2. That's essentially what it does. If that's unclear, so adjacency list of the pattern dot append the word. Okay, so that's our patterns to word dictionary, and all the items with the similar patterns, you will have all the same words. So okay, so we built our list. That's pretty simple. Okay, so now what we need to do, build a visited set, build visited set, so that they will not be visited again. So visited equals set, and we can put the beginning word in. Because maybe we put it in, maybe we don't. I'm not sure yet, but let's put it in, and so it will not be revisited, because we are starting our queue with our begin word as well for our BFS call. So we have a queue of words. Word queue, let's call it. I think that's a little bit more specific for the next reader, and they'll know what type of queue it is before even like working on it. I think it's just better. But you might think otherwise. Please let me know the reason why that is better otherwise, and we can write better code next time. So let's keep going. We have to have a count. So let's set the count at 0 or 1, because we have one word already. And we also need to return, if no pattern is found, return 0. Okay, so we're just taking care of the middle code, and once we're done, we are done with this problem. So let's take a look at that. So when are we gonna increment the count? Well, I think that's at the end of the word queue, after we fill in the queue of words with the second, with all the next BFS of words. So we're gonna do word pop. So for item in 4 words in word queue. So we're going to take one BFS call. So this is one way to take all the BFS calls for the everything inside, to make sure we empty the queue completely and get the next number of words into the queue. So I'm going to think about this for a little bit. Give me a pause, and I'll come up with a good word for it. Okay, I thought of the word. The word is queue item. Maybe it'll help next time, maybe it won't. But it's going to look at each queue item in the word queue for this particular length in word queue, the current length of word queue, and we're going to just iterate through all of these items once we have done that, and we won't increase the length of word queue. So I believe this should work. We're not gonna increase the word queue amount, and then that will change the word queue. But if it does, I would like to mitigate that by moving this here, but we'll get an error if that's the case. But I think it'll be more clear if we just say queue items equals length of word queue, and then we just take queue items. Yeah, I think if we just use I here, yeah, I think that looks good. That is perfect, I think. Okay, so we're looking at all the words that are running our BFS call, and what we're gonna do is add these words into our word queue. So let's take a look at all the patterns that are possible. So so let's get the word. So word is equal to word q dot pop left, so that pops the left item, and we have our word. So we're going to get all the patterns and find all the new words that we have to add to our to our word queue. So for j in range length of word, if so, we do the pattern again, and we're going to take the word if pattern in visited return, not continue. Otherwise, we're gonna visited dot add the pattern, and we're going to, I think I'm slowing down my thinking for now. It's been 26 minutes now, and my thinking slowed down a little bit. So let's see. I feel like the words are coming out of my mouth a little bit slower, but at this point, we need to take, we have all these patterns, and we need to get all the words from that pattern into our word queue. So word queue but do we want the same words though? Like, I mean, give me a moment to think about this. Like whether we should have patterns in our visited or queue. I think or like words, because we were thinking about that earlier, and we did not come to a conclusion whether having the word is better or having the pattern is better, because just because we haven't, the reasoning is it's unclear right now. It's because if we have a pattern, right, if we add a pattern to visited, right, and the pattern includes a word that we have seen before, do we still want to process that word? Maybe we don't. Anyways, I think we should do it both ways. I think either way would like find all the patterns that we would not want to look at anymore, and we would also find all the words that we will not look at anymore, and we will find out which one's faster or slower. But I think both ways do work. So we're gonna have to leave a note to try visited words and patterns to see which is faster. I think this is a very good thing to talk about during the interview, because it shows that you're thinking about like how we can make this code more efficient, and that you're weighing out the costs and the benefits of using either one. So word queue, with this is nice, because what we're gonna do is just add the items in our adjacency list in patterns. This is nice. This simplifies our code a lot. So just push that in, right? With that, we are basically completed our problem, and we've done everything item in the word list. So basically, that means that we have gone into this like BFS, and we have gone through both words, and we looked at the patterns. We checked. So we checked, and now what happened here is we've done our check. We popped our words. We popped both words. We looked at all the patterns, and if the pattern was visited, we're no longer looking at those patterns that will bring out these words. Maybe we should have visited words and visited patterns. Yeah, I'm actually thinking that we should do that. So visited word and visited pattern set. It's an empty. So visited pattern dot add pattern. And if um, if word in visited word continue as well. So let's move this word up, check, right? Otherwise, we're gonna word visited word dot add our new word, and that's gonna be our new visited word. And so we can now work on our pattern. Perfect. And if it's a visited pattern, then we would skip. So let's take a look at the visited pattern and do that. So pattern and visited pattern continue. Oh, there's a try comment, so let's remove that. And we have the visited pattern, which adds the pattern. Good. And word queue plus equals this particular pattern. Okay, looks good to me. So let's see. Oh, one more thing. So if word equals end word, right? Our end word, then return counts. Number of times we have brand or BFS call. So with that, I think we have completed this code. Let's run it and see how far we got. I'll have to take a pause because there might be bugs, and I will have to debug them. And this video has gone past 30 minutes, so pause. Hello there, and we are back. So this problem was that we had the beginning word in here in the visited words, and because we're checking both the visited words and the visited patterns, when we saw the visited word here, word and visited word for each queue item, well, we could say word here now, can't we? Because we know for sure it's a word queue, and for if it's a word index, I don't know, queue item, I think I is better. So that was the debugging for printing the adjacency list and printing out what went wrong to find out. So that we can get a clue about what's going on in the code that we didn't expect. So here we are. What we got here is queue item and word queue dot pop left. And now we have the number of times we should pop from the queue. Yeah, in range queue items. I don't know if that's the right word, like queue items. BFS round, I don't know. The queue items and we'll see how that works next time. But overall, I think this code works pretty well, and we were able to solve it in a pretty fast time. We handled both visited words, and we're handling visited patterns, so that we don't re-engage with the same words and same patterns. As you can see, it's pretty fast. Uses more memory though, because we are keeping a collection of the words and the patterns. And so the memory usage is pretty low. I mean, not low, pretty high. But I think this is better in terms of, splitting the difference between keeping only the visited patterns or visited words. Why not keep both, right? Okay, with that, we have completed the problem. If you have any thing to share, please comment below. If you enjoyed this video, like and subscribe. Want more videos, check the link in the description below. Thank you very much, and I will see you in the next one.